Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the channel Chandan Physics. In this video, we are going to discuss Joule Kelvin coefficient for ideal and van der Waal gases. Let's begin. It is another application of Maxwell's thermodynamic relations, means we derive Joule Kelvin coefficient for ideal and van der Waal gases by using Maxwell's thermodynamic relations. So, before starting that, we have to discuss what is the effect, what is the Joule Kelvin effect. Joule Kelvin effect that is basically known as Joule-Thomson effect. Joule Kelvin effect is known as Joule-Thomson effect. And the statement of that effect: when a gas under pressure is passed through a porous material, porous material means here we use cotton wool. Porous material to a region of lower constant pressure. The gas absorbs a change in its temperature. So, what is the statement of Joule Kelvin effect or Joule-Thomson effect? When a gas under pressure is passed through a porous material to a region of lower constant pressure, then what happens? That gas which passes through that of porous material absorbs a change in temperature, that is known as the Joule Kelvin effect or Joule-Thomson effect. Now, we have to discuss the thermodynamical process to that of Joule-Thomson effect, how thermodynamically the variables experienced. Thermodynamically, we observe that effect as the process which is Joule-Thomson experiment that takes place, the process in Joule Kelvin experiment takes place adiabatically. Adiabatically in the sense, here heat will be 0, constant heat. So, change in heat will be 0, that is dq is equal to 0, and the process is reverse, adiabatically and reversible. That is the condition under which Joule Kelvin experiment is performed. Now we apply first law of thermodynamics. We know from first law of thermodynamics dq is equal to du plus dw. Since the process is adiabatically, that's why dq is equal to 0 is equal to du plus dw. Or as we write here, since dq is equal to 0 as it is adiabatic. Now 0, that is d of u plus w, or 0 d w, that is the PV. U plus PV, that term is known as the enthalpy. U is the internal energy, P is the pressure, V is the volume. So that term is the enthalpy, as H, that is U plus PV, which is known as the enthalpy. The change in enthalpy is 0. So we can say here H is the constant. Thus, for any value of pressure difference that indicates, thus any value of pressure difference at the two sides of a porous plug what we observe, the enthalpy of the gas always remains constant. The enthalpy of the gas always remains constant, as we observe from that equation. H is constant. Now H is equal to U plus PV. Therefore differentiating both sides, we get dH is equal to du plus pdv vdp. These two are multiplied. du plus pdv, dS is equal to, that is dq plus vdp. That from first law of thermodynamics, dq is equal to du plus pdv. Here we know dH is equal to constant, H is equal to constant. So differentiation of H is equal to 0. The derivative of H will be 0 since H is constant. And from second law of thermodynamics, dq is equal to TdS plus vdp. What are the substitutions here? dH is equal to 0 as H is constant. and dq is equal to TdS. That means TdS plus VdP is equal to 0. Now ds in that of expression is perfect differential, and we know entropy is a function of temperature and pressure. Now ds in the above expression is perfect differential, and entropy S is a function of temperature and pressure T and P. Therefore, we write here entropy as a function of temperature and pressure. Therefore, ds is equal to del S by del T at constant pressure dt plus del S by del P at constant temperature dP. Now putting the value of ds in that equation. So what we have? Substituting the value of ds. Let us take it as equation number 1. Substituting the value of ds in equation 1, we get, just put the value of ds here. So that is T ds, that is del S by del T at constant pressure dt plus T del S by del P at constant temperature dP plus V dP is equal to 0. Now T del S by del T at constant pressure, that term is equal to Cp at the specific heat at constant pressure dt. Now del S by del P at constant temperature. So what are the substitution I write here? T del S by del T at constant pressure is the Cp, specific heat at constant pressure, and del S by del P, del S by del P at constant temperature is equal to minus del V by del T at constant pressure. That from what? That from Maxwell's relation. That from Maxwell's relation. So I substitute it, I write it minus V into alpha, where alpha is the value of del V by V divided by del T at constant pressure. That is from Maxwell's equation. That from Maxwell's equation. This is the Maxwell's relation. Maxwell's relation. These substitutions are implemented here. Cp dt, then minus Vt alpha what dP plus Vdp, Vdp is equal to 0, or Cp dt, that term to that side, that is V T alpha dP minus V dP, or Cp dt is equal to V as common. So, V, that is T alpha minus 1 dP, or dt is equal to V by Cp, Cp is divided here, and T alpha minus 1. Here alpha, the value is that, and that is the coefficient of expansion in of gas, that is the coefficient of expansion of gas, dP. That equation is known as the fundamental equation of the Joule-Thomson effect or Joule Kelvin effect of Joule Kelvin effect. Therefore, dt by dP, dt by dP, dt by dP, dt by dP is equal to V divided by Cp T alpha minus 1 dP that side. That equation is known as, that dt by dP is known as Joule Kelvin coefficient, that is the Joule Kelvin coefficient. Now, using that equation, means the Joule Kelvin coefficient, we have to derive the Joule Kelvin coefficient for ideal gas and for van der Waals gas. Now, this is the standard equation of Joule Kelvin coefficient. Now, for ideal gas, what is the Joule Kelvin coefficient? Taking 1 mole of ideal gas, taking 1 mole of an ideal gas, the gas equation PV is equal to nRT, n is equal to 1 here, PV is equal to RT, or V is equal to RT by P. Now, differentiating with respect to temperature at constant pressure. Now, differentiating with respect to temperature at constant pressure, we get, that is del V by del T at constant pressure is equal to R by P. Now, we use that value in the standard equation. Now, substituting that value, therefore we write the Joule Kelvin coefficient, the Joule Kelvin coefficient for an ideal gas is given by, so we get dt by dp, dt by dp is equal to v by cp, v by cp and T alpha. Alpha del B by B del T at constant pressure, del B by del T at constant pressure. So the terms are looking like this. Right, that is 1 by Cp T del V by del T at constant pressure minus B. Okay, here I use another one, the Joule Kelvin coefficient, that is the derivation from here. That form also can be equalized to 1 by Cp T del V by del T at constant pressure minus V. That is equal to dt by dp. That is equal to dt by dp here. That term means I just relate that one here. So putting this, no confusion about this, just substitution of alpha here. T del V by del T at constant pressure minus V, that is 1 by Cp T del V by del T at constant pressure, that is R by P. So R by P minus V, 1 by Cp Tr by P, RT by P, that is V, that is V minus V. The result will be 0. We get dt by dp, that is the Joule-Thomson coefficient is 0. Therefore, Joule-Thomson or Joule Kelvin coefficient is 0 for a perfect gas. For a perfect gas, the Joule Kelvin coefficient is 0 for a perfect gas. dt by dt is equal to 0 here for a perfect gas. We use the standard equation of Joule Kelvin coefficient. Now, what should be the Joule Kelvin coefficient for Van der Waals gas? For Van der Waals gas, here we take 1 mole of real gas, taking 1 mole of real gas, the gas equation of Van der Waals is it is P plus A by V square into V minus B is equal to RT, where A and B are constant as we know it. Expanding that bracket, so PV minus PB plus A by V minus AB by V square is equal to RT. Since the Van der Waals constant A and B are very small quantities in comparison to that of large quantities V square, so that term is neglected. So we have PV minus PB plus A by V is equal to RT, as AB by V square is neglected. Now PV is equal to RT plus PB minus A by V, or V is equal to in place of V, it is RT plus PB minus V can be substituted as V is equal to RT by P. So that is A P by RT. PV is equal to RT plus P as common, B minus A divided by RT. Now differentiating that above equation with respect to temperature and keeping P as constant. Now differentiating the above equation with respect to temperature, keeping P as constant, we get P del V by del T are constant pressure, that is R plus first term PB term will be 0, only that term, so it will be T square minus plus, so AP divided by R 1 by T square, its differentiation with respect to temperature, or del V by del T or constant pressure is equal to R by P plus A by R 1 by T square. Del V by del T at constant pressure is equal to R by P plus A by RT square. Now substituting the value of this with the Joule-Thomson effect or Joule Kelvin coefficient standard equation, therefore we get the Joule Kelvin coefficient for Van der Waals gas is given by dt by dp is equal to 1 by Cp T del V by del T at constant pressure minus V. That is the standard equation. This is the standard equation. dt by dp is equal to 1 by Cp T del V by del T minus V, which is, that is the short form of alpha. Just substitute the value of alpha here, nothing. Now putting the value del V by del T at constant pressure here, 1 by Cp, that is T R by P plus A divided by RT square minus V is equal to 1 by Cp RT by P plus A by RT minus V. Here RT by P, we know RT by P is equal to V minus B minus A by RT. Look at the equation previously as you derived. RT by P is equal to V minus B minus A by RT, as V is equal to RT by P. Now putting the values here, one by Cp in place of RT by P, I substitute V minus B minus A by RT plus A by RT minus B. One by Cp minus B, B cancel out, minus B, that minus minus plus, that is 2A by RT plus 2A by RT. Thus we get dt by dp is equal to 1 by Cp 2A by RT minus B. This is the Joule Kelvin coefficient for actual gas, or we can say the real gas, that is this is the Joule Kelvin coefficient for real gas or actual gas, or we can say the Van der Waals gas. So with the help of this video lecture, we understand one of the application of Maxwell's thermodynamic relation, that is Joule Kelvin coefficient for real and Van der Waals gases. We say what is the treatment of Joule-Thomson effect or Joule Kelvin effect, and the mathematical equation we derive thermodynamically. And finally get the fundamental equation of Kelvin, Joule Kelvin effect, and that equation is the Joule Kelvin coefficient, that is the necessary one, that is dt by dp is equal to 1 by Cp T del V by del T and constant pressure minus B, as we substitute the constant alpha here, that is the coefficient of expansion of gas. So for ideal gas, the Joule Kelvin coefficient is equal to 0. Now for Van der Waals gas, the Joule Kelvin coefficient that much. So with this useful and informative notes, let me wind up this session. Thank you.